Welcome to the How to Optimize a Gas Turbine Cycle tutorial. This tutorial is part of the tutorial series dealing with more advanced topics on the use of the gas turbine performance software GasTurb. In this tutorial, we will learn how to conduct optimizations with GasTurb using the integrated optimization functionalities. The tutorial starts with a short introduction to the GasTurb optimization tool. While applying this tool to different gas turbine configurations, we will learn how to optimize a gas turbine cycle with several optimization variables simultaneously and how to use additional design constraints, which help us getting realistic results of the optimization. Additionally, we will learn how to consider critical off-design conditions in the design optimization process. For our first optimization, we will use a simple turbojet engine. We select the turbojet from the Jet Engines tab and choose the configuration without afterburner. We keep the pre-selected performance scope and click on Design to open the Design Point Input window. Before starting our optimization, let us have a look at the initial design point. A usual target of a gas turbine cycle design optimization is the specific fuel consumption. As we know, a design variable with a strong influence on the specific fuel consumption is the compressor pressure ratio. The summary shows us that with the initial pressure ratio of 12, a specific fuel consumption of 25.1 grams per kilonewton second is achieved. A parametric study of the pressure ratio in a wide range from 10 to 100 shows us the influence of the pressure ratio on the specific fuel consumption. As we see here, the minimal specific fuel consumption is reached at a pressure ratio of approximately 65. Our goal now is to find the exact optimal pressure ratio for which the specific fuel consumption is minimized by using the optimization tool of GasTurb. We select the task Optimize. The Input for Optimization window appears in which we can set the variables, constraints, and the figure of merit for the optimization. First, we need to select our optimization variables. GasTurb allows us to define up to 12 of them. For our first optimization, we stay with only one variable and drag the variable pressure ratio to the input grid. Next, we enter boundaries for the variable. The pressure ratio of the initial design point calculation is stated in the column Start Value. The minimum value must be lower, and the maximum value must be higher than the start value. We set a minimum pressure ratio of 5 and a maximum pressure ratio of 120 for our optimization. Finally, we switch to the tab Figure of Merit to define the objective of our optimization. We select the property-specific fuel consumption, drag it to the field Figure of Merit, and select Minimize. We start the optimization process by clicking the Run button. The optimization window appears. Here the specific fuel consumption of the initial cycle is shown, which we now want to minimize. There are 4 strategies available in GasTurb for finding the optimal design point: Random, Endless Random, Systematic, and New Start. The random search strategies will find an optimum by exploring random values of the design variable around the best solution found previously. The systematic search uses a gradient search algorithm. From the given start point, it begins in the direction of the steepest gradient. As soon as the best solution in the direction is found, the direction is changed by 90 degrees. Again, looking for the highest point. Connecting the start point and the optimum point of the second direction. The next direction is defined and followed as long as the values improve. This procedure is reapplied until an optimum is found. In case of more complex optimizations with a restricted solution space, it is of higher probability that the described search strategies can only find a local optimum. In order to make sure that the global optimum is found, automatic restarts using new starting points of the optimization can be set. A new starting point for the random search strategy can be selected via New Start. Further information about the search strategies can be found in the GasTurb manual. For our optimization with only one variable running a simple random search is sufficient. Let's start the optimization. After the optimization is completed, we open the output window of the optimized cycle via clicking Optimum. As we can see, the minimum specific fuel consumption is achieved at a pressure ratio of about 65. This corresponds to the result previously found in the parametric study. However, this gas turbine cycle is unrealistic for a one-spool turbojet engine as, for example, the turbine pressure ratio is around 24. To achieve realistic results, we define constraints for the optimization. We close the optimization window to restart the optimization process. When closing the optimization window, we can decide to reset the input data to our original design point, or to use the new optimized cycle as our new design point. We proceed with our original design point. We leave the variable and the figure of merit as they are and introduce the turbine pressure ratio as a constraint. We limit the turbine pressure ratio to values between 1 and 4, which are more reasonable values for a single-stage turbine. Now, let us run the optimization again. We can see that a much lower optimal pressure ratio of approximately 16 is reached. The value of the optimization constraint, the turbine pressure ratio, is approximately equal to the limit we defined before. This means that the optimal pressure ratio for minimal specific fuel consumption is now limited by the turbine pressure ratio. We click on Optimum again to see the results of the optimal cycle. With our optimized design point, we were able to reduce the specific fuel consumption by about 6% compared to the initial design. When there are only one or two variables, the optimization is usually straightforward. In this example, a parametric study would have given the same result. Next, we go for a more complex task, optimizing the gas turbine cycle of a turbofan engine, introducing additional variables and constraints. This would require many parametric studies to find the optimal solution. We will see that GasTurb's optimization tool quickly identifies the optimal cycle. Let us close the optimization and return to the Welcome window to select the new engine configuration. In the Welcome window, we select the engine configuration Geared Turbofan and choose the configuration with a gear ratio of 1. We click on Design and have a look at the initial design point. The specific fuel consumption for the initial design point is 16.6 grams per kilonewton-second. Let's close the output window and optimize the cycle for a minimal specific fuel consumption. In this case, we want to optimize 5 free design variables of the 2-spool turbofan engine: the inner and outer fan pressure ratio, the bypass ratio, the intermediate compressor pressure ratio, and the burner exit temperature. Reasonable minimum and maximum values are already entered in the table on the right. In addition, we define several constraints for the optimization. Our engine should not exceed a low-pressure turbine temperature limit of 1,300 Kelvin. We also limit the maximum achievable pressure ratio of the low-pressure turbine to 12, for example, due to a limited number of turbine stages. Finally, our engine should deliver at least a thrust of 31 kilonewton. Note that we need to define a minimum and maximum value for each parameter, even though only one of the values might be relevant. As our figure of merit, we define minimum specific fuel consumption. Now we can run the optimization. We see that the solution is limited by all 3 design constraints. This means that these are important boundary conditions and should be carefully defined in the early stages of the engine design process. Let us have a look at the optimal gas turbine cycle. With the optimization, we achieve a reduction of the specific fuel consumption by 4.7%. It should be noted that our optimized design has a higher turbine inlet temperature and a higher compressor pressure ratio than the initial cycle. For a comprehensive evaluation, we should also consider a change of cooling air mass flow and compressor efficiency during our optimization. This could be done using composed values and user-defined iterations. For now, we have optimized the cycle for minimum specific fuel consumption, considering several limitations at cruise conditions. However, we did not consider off-design points that might limit the engine design as well. For example, the LPT inlet temperature limit during a hot day takeoff can be a limiting parameter and should therefore be taken into account during the design optimization. For defining such an off-design constraint, we return to the GasTurb main window and switch to off-design. We select Mission and start the task. The Mission window appears, in which we can define various off-design conditions of the engine during a flight mission and simulate them simultaneously. For our design calculation, we want to consider the off-design conditions for a hot day takeoff, with a required takeoff thrust of 145 kN. We run the single-point mission. The mission point can now be used for the design optimization process. Now, we close the mission window and switch back to the design calculation. We conduct another optimization. We click on Constraints. A new drop-down list is shown on the right, which is only visible if an off-design mission point is defined. HDT represents the hot day takeoff point that we have just defined. We select HDT and apply a constraint for the LPT inlet temperature for the off-design condition. GasTurb now additionally calculates the off-design performance at hot day takeoff during the design optimization and checks if the limit is met. Again, we run the optimization. Let us check the new optimal design point. The net thrust and the LPT pressure ratio still limit the optimal design point. However, for the LPT inlet temperature, some margin is kept to satisfy the hot day takeoff requirements. The specific fuel consumption at the design point is now reduced by 3.9% compared to the demo file's design point, whereas without the off-design constraint, the reduction was 4.7%. The additional constraint on the LPT inlet temperature, 1,300 Kelvin during hot day takeoff, reduces the feasible solution space of the optimization, shifting the optimum to a point with higher specific fuel consumption. When closing the output window of the design point, the output window of the off-design point during hot day takeoff is shown. For these conditions, the limit of the LPT inlet temperature is reached. This concludes the How to Optimize a Gas Turbine Cycle tutorial. We learned how to use GasTurb's optimization tools to reach optimal cycle designs, considering several boundaries and optimization variables, as well as critical off-design conditions. With these practical tools, GasTurb enables us to quickly find an optimal cycle design for our specific use case. For more detailed information on how to optimize cycles in GasTurb, the GasTurb manual offers extensive guidance. There are further tutorials covering a wide range of GasTurb's tools and functionality. Pick any tutorial that you are interested in. We hope you have a great experience using GasTurb. In case of questions, don't hesitate to contact us.